I hope you're enjoying this continued lesson on torsion. Now I want to talk a little bit about how we deal with torque and gear ratios and power in different mechanical systems. So what's a great example of where we see gears? Well, I think it's time I introduce you to our clock friend here. And so the clocks are actually pretty cool, and they have a lot to teach us about gear ratios and power. Because believe it or not, this clock can run for 8 days with no electricity, no batteries, no nothing, just mechanical power. And so how do we gain that mechanical power? Well, we come in and we have what we call a key. So this key goes in and we put it in here and we twist. And what we're doing is we're twisting a torsional spring. And this torsional spring will slowly bind up, and then over the entire 8 days it slowly releases, and that powers the gears, and then that causes the pendulum to rock back and forth, and that'll help control how quickly the power is let down from the gears, from the springs, and then the clock runs. So it's pretty cool. So this is how we power it. It's got two main springs. The two main springs, one powers the clock and one powers the chime. So it's pretty cool, pretty interesting. If you're even more interested, you can see that in order to twist this, I have to apply a torque, right? I apply a force couple to this butterfly kind of attachment to the key, and that causes torque or twist. So, fun story, one morning I was doing this, and I was applying the torque, and this is what happened to our key. So if you're wondering what a torsional failure looks like, this is a good example. You can see that this used to be the key, and then I was just twisting and it broke. You can see along the edge here, it was kind of a brittle fracture. It kind of follows a little bit of a helical path because it was under shear stress that ultimately caused it to fail. You can see here, this is a good example too of a cylindrical shape that we might be doing a lot of our analyses on, especially when we talk about like calculating J and polar moment of inertia and stuff. So it's a good example. If you just want to see another example of a torsional failure, this is another torsion specimen. So this is much like our tension specimen, except we would grip this in a machine and we would twist it and break it in torque. So here again, you can see kind of that messy, a little bit of a helical pattern here. And again, if you zoom in, hopefully you can see that. You should see that it has a very rough edge to that surface. And so that rough edge tells that it's typically a fast fracture. It wasn't very ductile. It was a very brittle fracture because it just suddenly went and broke. And you can even see that by the deformation. That would be opposed to a more ductile failure. So we can have shear failures that are ductile. And this would be more of an example of that. So this is another specimen that was put into torsion, and hopefully you can see here that it didn't break, it just twisted, something like this. I'm thinking about patenting this or something and making it like jewelry or something that you can wear. But anyways, torsion is pretty beautiful if you ask me. We want to go ahead and talk a little bit more about how we gain power and can have torque advantages due to gears. So I want to take you back to our clock, and we're going to take a look inside. Let's explore more about power and gear ratios by taking a look at how our clock actually works. So if we open up the back, we can take a look at the inside mechanisms that are powering this clock and keeping it running. So we see, I talked about the torsional springs. That are these guys right here. So this is what we wind up, and you can see that as we coil it and wind it, it gets a tighter coil. So that'll slowly open throughout the week, and that'll turn the different gears that are attached to it. Those gears are all connected by other gears and gear shafts and a bunch of different rods, and it goes back and forth, and it comes up to here, and then that's where the pendulum comes in. The pendulum rocks back and forth, And so it helps control how quickly these gears turn. Because if we didn't have the pendulum in place, the gears would just rotate, everything would rotate, and it would lose all its power at once. So by connecting it back and slowly letting down the power, we can keep our clock running all week. This thing here is just the chime. So when the time comes, some of these gears move the mechanism right here so that our clock will chime. So this will shift up and then strike our, strike the chime. So that's kind of how the clock works. I want to take a look at power and see how we can use kind of revolutions and rotations in systems and relate that back to our power that's supplied. As engineers, we define power as the work per unit time. And if we remember work from our physics or science class is equal to a force times a distance. So when we talk about power in terms of this spinning system, so this gear shaft that's spinning, our power will then be the torque is our force, and then we have to multiply it by our distance. But our distance is going to be a rotation, and we'll say at one instant in time, it would be d theta. And then it's per unit time, and we'll say that this is ds. So this gives us then d theta ds. D theta ds will be what we call the angular velocity. So how fast the gear shaft is rotating with time. So this would be revolutions per minute or something like that. So that gives us our formula for torque. Again, omega is our angular velocity of the gear shaft. All right, we can see some of the units here. So in SI units, we work power is in watts, and then in the US customary unit system, power is in horsepower. So this is something we're familiar with if you're into mechanical engineering and into your car, especially, you know about horsepower. And we can go through and look at using the frequency. Frequency is a cycle per second, so it's just another way of describing speed. And so we can look at the angular velocity as 2 pi radians times 1 cycle per second. So that gives us times our frequency. So we can rewrite our formula. Power equals 2 pi F times our torque T. If you go on to study mechanical engineering, you'll be dealing a lot with power and torque. So you'll be learning more about this in the future. For now, we're just kind of doing the introduction to this topic. Now that we know how power and torque are related, let's examine further about gear ratios and see how we can use gears of different sizes to help scale the torque up and down from one gear shaft to the next. So engineers use this a lot. Whether you're using this in your car, perhaps in your transmission is maybe where most of us encounter this day to day, or if we come back to our clock, we're using a bunch of different gear sizes to help power up and power down those torques from one gear shaft to the next. So let's talk about the gear ratios. The gear ratios allow the engineers to scale power and torque from one gear shaft to the next. So we can take advantage of the use of gears to amplify our torques from one gear shaft to the next. So this is very useful when trying to transmit, maybe a higher power to a different element of our system. We see this especially in cars, right? We have our transmissions in our cars. We can use different gears for different efficiencies at different speeds. So to come up with this ratio, this gear ratio, I want to consider a torque, TA, applied to gear A. So this is going to be a torque that's going to cause gear A to rotate. Now, if this was in static equilibrium, gear A would be kind of held up, and there would be a force that's holding that gear in place. And that force I called F gear, and I labeled it here on my picture. I also want to label the geometry. I have the radius of this gear. So the radius is going to be RA. All right, if I want to equate the torque to this force at the gear tooth, we know that torque is a force times a distance. So this force at the tip of the gear tooth times the radius of the gear will have to equal the applied torque. So F gear times the radius of A is going to equal the torque at A. All right, so that's what's happening on gear A, right? But then we have to look at what happens on gear B. If we have this force at the gear tooth, that means that we have an equal and opposite applied force at the gear tooth on gear B. And that force is going to cause gear B to rotate clockwise, as we're looking at it here in this particular picture. So the force at the gear is going to start causing a rotation in gear B. Hopefully gear B would be in equilibrium in our case for mechanics and materials, but it doesn't necessarily have to be the case. This whole thing could be a spinning system. If we look at the torque at B, we know that the torque at B also, like for gear A, the torque at B has to be equal to F gear times the radius of B. And so let's go ahead and sketch that radius in place. All right, because at the interface where these two gear teeth touch, we only have Newton's law, third law of motion, where, for every action there's an equal and opposite reaction. So right at the gear teeth, we have F gear on both sides, and they have to be the same. So F gear must be the same on both of these gears, both gear A and gear B. And so if we set F gear equal to each other, so in the first one, we solve for F gear equals the torque at A divided by the radius of A. And in our second scenario on gear B, F gear equals the torque at B over the radius of B. So let's jot that down. I'll even include my colors here so you can help correlate the radius with a distance and the torque with a force. All right, we can rewrite this as the gear ratio, right? So the gear ratio is going to be a ratio of the radii of gears A and B. So if we rewrite this formula, this portion down at the lower right-hand side, we can rewrite it as the radius of A over the radius of B would then equal the torque of A over the torque of B. And so this is what we refer to as the gear ratio. And we see that we can relate the torques. So the torques in both gears aren't necessarily going to be the same. They're going to be either scaled up or scaled down depending upon the ratio of the radius of these gears. We can repeat this process for the angle of twist of both of these gears. I'm going to sketch in here a displacement, so the displacement here at the gear tooth, and we want to relate that displacement at the gear tooth back to the angle of twist of gear A. We're also going to relate the displacement at the gear teeth to the angle of twist at gear B, and you can see since visually you can see the angle at B looks like it has to be a lot more. Gear B is going to rotate much further because it has a smaller radius. And so we can prove that by just coming up with a way to calculate that deflection. I'll say that vertical deflection is delta, and the delta must be the same for both gears. So delta for gear 1, gear A, will be the radius times the angle. So this goes back to our arc length formula. And again, for small displacements, we'll assume that the arc length is roughly equal to the straight line distance. This has to equal the radius of B times the angle of twist that gear B undergoes. And so we can then rewrite this in terms of our ratio, again, of RA over RB. And that will give us RA over RB equals phi B over phi of gear A. And so we see that we have slightly the opposite relationship. So whereas when we're going from a larger gear to a smaller gear, the torque gets smaller. When we go from a larger gear to a smaller gear, the angle of twist increases. I hope you found that very interesting. I think it's very cool how you can use different radii for the gears, and then that'll help determine how your torque scales from one gear shaft to the next. So now we want to apply this. So I've kind of isolated maybe 2 gear shafts in our clock here, and I've drawn up a little problem. We'll check that out in this coming example. So go ahead and give it a try and see how we can use the formulas we just took down in our notes and apply them to solve some engineering problems. Here we go. You can go ahead and read through the problem statement. I just kind of reiterate some of the things about the clock movement. But I've taken one segment of the clock and illustrated it here. So we see that there's some sort of torque applied to the gear at C that's causing rod ECDF to start spinning. That will cause gear D to spin, which will lock into gear B. Gear B will try to rotate, but then it'll lock in because it's fixed at point A. So hopefully you see that happening. E and F are just frictionless bearings that are just holding the rod up, so it's not just suspended in mid-space. All right, I've gone ahead and illustrated what I mean here. As the torque is applied at C, there's a torque at D that's rotating, and it's also going clockwise, and then that's going to cause a torque on B that's going to be counterclockwise, because remember, at the gear teeth, we kind of switch direction. When one's rotating clockwise, the other switches direction and rotates counterclockwise. All right, we're asked to determine the shear strength in the different segments, so in segment CD and AB, and we're also asked to calculate the angle of twist at gear B and at gear D. So we'll start with shear stress in these members. So we can take a look and we can say, okay, well, what's happening in the different members? So I think if we look at the shear stress in AB, we know our shear stress formula relies upon the torque. So we're going to have to figure out the torque in each of these segments. So the torque in segment AB is just going to be whatever the torque that's being applied to gear B is. But we don't really know what that torque value is quite yet. In terms of our torque along segment CD, we know that whatever torque is being applied at C is also being transmitted to D. And so our torque along that segment is going to be 0.5 newton meters. I've gone ahead and just put absolute value signs in it because, as we're isolating kind of a spinning system, it's a little bit hard to kind of keep track of our directions. And, when we talk about shear stress, ultimately, if the shear stress is exceeded, if it's spinning clockwise or counterclockwise, it's not going to be as critical because, at least for most metals, the shear strength will be the same in both directions. All right, so our torsion formula says the torque, the shear stress equals the torque times the radius over J. So in segment CD, we have that the torque is 0.5 newton meters. We multiply by the radius. We see that we're given that the diameter of rod ECDF is 4 millimeters, so the radius is 0.002 meters, or 2 millimeters. And then J is pi over 2 times the outer radius to the fourth minus the inner radius to the fourth. But since these are solid gear shafts, we just have the outer radius to the fourth. And we do our math, and we get that the shear strength along segment CD is 39.789 megapascals. All right, so hopefully that part was straightforward. We're getting hopefully comfortable with calculating shear stress in the different members and just keeping in mind that we have to first figure out what the torque is. If you wanted to draw a torque diagram, you're more than welcome to, in this case, to go ahead and sketch that torque diagram for this rod. Now on to using the gear ratio. So we know that the torque at D and the torque in B are related using our gear ratio. So that tells us that the radius of B over the radius of D equals the torque of B over the torque of D. And so if I set the radius of B, which is 15 millimeters, over the radius of D, which is 6 millimeters, I'll set that equal to the torque at B divided by the torque at D, and we know that the torque at D is going to be the 0.5 newton meters. So the 15 over 6 is really our scaling factor. So when we move from a smaller gear to a larger gear, we increase our torque. So the torque at B is going to be increased from the torque on D by a factor, in this case, of 2.5. That's actually pretty significant. That's a pretty large increase. just from changing the gear sizes on our system. So doing the math here, the torque at B is going to be 1.25 Newton meters. All right, so hopefully you have an appreciation now for how we can amplify the torque from one gear shaft to another just by changing the radius of the gears where they interlock with one another. We can go through and do our shear stress formula for segment AB. So that's going to be the torque on segment AB over rho A, or times rho AB over the polar moment of inertia of AB. So we have 1.25 Newton meters times the radius. The radius of segment AB is going to be 4 millimeters. So again, 8 millimeter diameter, so 4 millimeter radius, and that's 0.004 meters. And then J is pi over 2 times 0.004 meters raised to the fourth. So if we go through our math and we do our calculations, we should get that the shear stress on segment AB is 12.434 megapascals. All right, not that the question asked us, but this falls well within the range of yield stress for brass. So most clock parts are made from brass to kind of help with corrosion long term. And so these values both fall well below the yield stress of brass. So our system should work well into the future and help keep us on time. All right, parts B and C asked us for information of the angle of twist. So we want to find the angle of twist at B. So whenever I work angle of twist problems, I always like to start at our fixed point. And so we see that our fixed point is point A. And so then I can kind of, starting from where I'm fixed, I can start shifting out to find the angle of twist at different parts in the system. So the angle of twist at B would equal the angle of twist at A plus the angle of twist of B relative to point A. And so since point A is fixed, the angle of twist is 0. And then we go through and we'll do our formula for the angle of twist at B relative to A, which will be TL over GJ for segment AB. So now we just need to substitute these values for segment AB. So we see that the torque on segment AB is 1.25 Newton meters. The length of segment AB, we want to go back up and check our problem. I believe it's 60 millimeters. And so that would be, if we convert this to meters, it would be 0.06 meters. So we'll double check those lengths. In the denominator of this equation, we have the shear modulus. So we're using the shear modulus for brass, which is given to us in our problem statement as 40 gigapascals. So that's 40 times 10 to the 9th pascals. And remember, 1 pascal equals 1 Newton per meter squared. So I'll go ahead and put this into my equation as 40 times 10 to the 9th newtons per meter squared. Finally, we have J. I'll just do the calculation directly in my problem statement. J is going to be pi over 2 times the radius to the fourth. And in this case, segment AB is the larger diameter rod. And so it's going to have the 4 millimeters or 0.004 meters raised to the fourth. So we do our calculations and we can calculate the angle of twist at point B. I have 0.004663 radians. So remember, this is unitless, so it comes out in radians. And we can convert radians to degrees by multiplying by 188 divided by pi. And that will give us 0.267 degrees. Again, I'm going to look back to my picture. Remember, I drew in the torque at B. I said that B was going to be rotating counterclockwise. And so that's the direction that the angle of twist at B will also be rotating. Finally, we want to get the angle of twist at point D, and again, we're going to have an opportunity to use our gear ratios to come up with this calculation. So because gear B is the larger gear, when it rotates through an angle, the smaller gear, in order to keep up, has to rotate through a larger angle. So we'll set up our gear ratio that says that the the radius of gear B divided by the radius of gear D equals the rotation, the angle of twist at gear D divided by the angle of twist at gear B. And so this is opposite of torque. So remember, as we go from a larger gear to a smaller gear, the angle of twist will be increased. But when we go from a smaller gear to a larger gear, the torque gets increased. We can see this in the math that follows. So if we solve for the rotation at gear D, that will then equal the radius of B over the radius of D times the angle of twist of B. And so our gear ratio, radius of B over radius of D, was 2.5. So the angle of twist at point D is going to be 2.5 times the angle of twist at point B. So 2.5 times the number given above gives us that the angle of twist at point D is 0.011657 radians. And again, if we convert this to degrees, then it would be 0.668 degrees. This rotation will be clockwise because, again, if we're following the system and thinking of it kind of dynamically, as gear C rotates, gear D is also trying to rotate clockwise. Or we can just look at the gear teeth. As gear B rotates counterclockwise, gear D has to rotate clockwise because at the gears, the motion switches direction. The torque will switch direction. Well, I hope you enjoyed our problem and our talk that kind of surrounded our clock. I think, just like soda shops are a thing of the past, a lot of times these very cool clocks that, run without any kind of battery or electricity, they just run off of mechanical energy. I feel like these are something from the past too. But hopefully you've taken a little bit of interest in it. I take a particular interest in this because actually my father-in-law, he fixes and repairs clocks like this all the time. So he actually fixed this clock for my wife and I. So it's very cool. And I think it's very interesting and very applicable to mechanics and materials.